Hello everyone, I'm Wang Shaobu from Tsinghua University. I'm glad to be here to introduce our research work, namely understanding silent data corruptions in a large production CPU population. This is a collaborative work from Tsinghua University, the Ohio State University, and Alibaba Cloud. Distributed systems have a rapid development. Firstly, the number of processors in a system can reach millions. Secondly, each processor becomes more complex. Semiconductor lithography process of the processor can achieve 3 nanometers. As a result, distributed systems face the challenges of multiple taps and a large quantity of processor faults. Here we present a real-world case of processor fault in our production services. One day, we found a catastrophe occurred. The performance of one service degraded hardly. We later attribute it to a series of silent checksum corruptions, namely they are corrupt without any notification. We start a debugging routine to check our disks, memories, and softwares. However, no fault was found. And after a several-week-long tedious fault tracing work, like analyzing system logs, we finally identified the root cause. Some processors in our system miscalculated the checksum intermittently. And this is just a case. Similar issues continuously occur in the production. We call such CPU cost errors that occur without immediate notification or obvious indication as CPU silent data corruptions, also known as CPU SDC. Such errors originally come from logic bugs and manufacturing defects of faulty processors. Most of these bugs and defects can be eliminated by high-volume manufacturing testing. However, some of them can still escape from testing because of limited manufacturing testing resources. These escaped faults enter the production and lead to catastrophes, such as data losses and wrong responses. Many companies have noticed this issue. However, existing knowledge about CPU SDC is not enough. The detailed measurement as well as systematical analysis are still lacking. This is mainly because CPU SDC are hard to capture due to their relatively low failure rate, as well as an absence of large-scale system experiments. Our work has 3 contributions. Firstly, we report the prevalence of silent data corruptions via large-scale testing. We performed 32 months of continuous testing on over 1 million production processors in hundreds of clusters stretching across the world. Furthermore, we investigate real SDC cases in depth. We give quantitative analysis from multiple perspectives, including software tracking condition, reproducibility, and so on. Besides leveraging observations in our study, we propose an efficient tool for SDC mitigation named Farun. Here is a roadmap of our 12 observations. These observations can be divided as 4 groups, namely the prevalence of silent data corruptions, the software symptoms, the reproducibility, and the performance of existing strategies while facing CPU SDC. Now I will introduce 7 of them. More details about other observations can be found in our paper. First of all, CPU SDC is not just a black swan event. We report the overall failure rate of the processors identified to cause SDC is 3.61 per 10,000. Furthermore, in our testing, we choose 3 test timing pre-production, namely factory delivery, data center delivery, and reinstallation. And as for online services, we regularly test these processors every 3 months. Although many tests are performed pre-production, we still encounter SDC online. Besides, every microarchitecture in our fleet has faulty instances. The failure rate varies from different microarchitectures, and we plan to study the reasons in the future works. These observations suggest that system designers need to pay enough attention to CPU SDC. Secondly, although we have tested most features of our processors, we only observe SDC in following features, namely arithmetic logic operations, vector operations, floating point computation, cache coherence, and transactional memory. It is possible that compared to other features, such as low store queue and branch instructions, these features are indeed more vulnerable due to their complexity. And it is also possible that other features are equally or even more vulnerable. But faults in other features tend to directly cause crashes rather than silent data corruptions. Either way, systems can implement fault tolerance aimed at specific workload operations to reduce strategy overhead. Thirdly, we observe bit flips are not evenly distributed across all positions. For floating numbers, as an example of the figure, bit flips mainly occur in the fraction part. As a result, these errors incur minor precision losses. For example, the majority of precision losses of double precision floating point numbers are less than 0.02%. This observation suggests that system designers need to rethink strategies that have been designed under traditional assumptions about bit flip patterns. Another observation is about reproducibility, which is measured by error occurrence frequency. The reproducibility of SDC varies a lot. Some error can reproduce nearly each run, but other errors may need hours to reproduce. And we observe temperature serves as an important triggering condition. The reproducibility of some SDC demonstrates exponential growth with increasing temperatures. The figure shows an SDC example, and we measure the reproducibility of this SDC on different temperature. We carry out experiments on defective core, and to make temperature constant, we use cooling devices to lower the temperature and use stress workloads on other cores to raise the temperature. We can see that the logarithm value of reproducibility has a strong linear dependence on the temperature. And this observation suggests that systems can mitigate SDC impacts by the temperature control. And we can use this feature to mitigate SDC in a smarter way. In another word, we can incorporate both proactive SDC testing and temperature control. This figure shows the minimum triggering temperature of different SDC and their corresponding reproducibility. We find SDC with a low triggering temperature tend to have a high reproducibility. As a result, testing is suitable to these areas, while control is costly. This is because application can easily reach triggering temperature, and thus control operations will be frequently activated, which impacts the performance of the application. On the other hand, SDC with a higher triggering temperature tend to have a low reproducibility. As a result, control is suitable to these areas where testing is costly. This is because more testing resources are required to reproduce errors. To summarize, we call the first type as apparent ones and the second type as tricky ones. As shown in this slide, using different mitigation strategies for different types is going to be more effective than using a single strategy. We also give observations on assessing performance of existing strategies, including fault tolerance techniques and proactive SDC testing. Testing toolchain we use is provided by the chip manufacturer. It includes a framework and hundreds of test cases. These test cases are programs carefully crafted with consideration of both software behaviors and hardware features. The framework drives these test cases. allocate testing resources, as well as check error occurrence. We observe that existing testing strategies need to be improved. Firstly, most test cases have not detected any errors in production testing. Secondly, existing toolchain fails to detect some SDC cases. That is, these errors need complex multi-thread conflicts. This observation suggests that testing can be improved from two perspectives. Firstly, testing can prioritize some test cases with the help of historical testing data. For example, if we have observed that a certain type of CPU SDC, certain test cases, or a certain feature, we can prioritize our test to focus more on such test cases or feature on this type of CPU. Secondly, testing needs more effective test cases, especially in multi-thread scenarios. Based on our observations, we designed an efficient SDC mitigation tool named Farong. The key idea of Farong is relying on prioritized testing to test a highly reproducible SDC and relying on temperature control to mitigate less reproducible SDC. Farong has three designs, namely adaptive temperature boundary, efficiency-focused SDC testing, and fine-grained processor decommission. These designs are all inspired by our observations. I will introduce the adaptive temperature boundary, and the details of the other designs can be found in our paper. As we have mentioned in observation about reproducibility, we can incorporate testing and control for better SDC mitigation. To achieve this, Farong sets a temperature boundary. If application temperature reaches above this temperature boundary, controls will be activated. That is, Farong will operate cooling devices to give more cooling ability. And if this still cannot lower the temperature, Farong will reduce the CPU utilization of the application. And Farong also performs SDC testing to mitigate errors whose triggering temperature is below this temperature boundary. However, given the situation that the normal working temperature of the application can reach above this temperature boundary for a long time, application will be frequently disrupted by the control operations, which influence the application performance. Farong assigns the highest priority to application performance, and under this situation, Farong adapts the boundary based on the working temperature logs. As a trade-off, Farong needs to perform more testing since it needs to detect more tricky SDC. We also perform a series of experiments to evaluate Farong. Our baseline is default SDC testing configuration used in Alibaba Cloud, and we simulate workload operations that impacted by CPU SDC via our toolchain. We run these experiments on 40 processors found in production services, and compared with the baseline, Farong achieves lower overall overhead and better testing coverage of SDC. Now let's conclude this report. CPU SDC have become a non-negligible issue for modern systems. We perform large-scale testing and in-depth investigation to study CPU SDC. Our study presents 12 observations, and based on these observations, we propose an efficient mitigation tool named Farong. Our study opens many directions on future research. For example, there needs study on exact SDC impaction on different applications, such as how the minor precision losses impact the computation services. There also needs study on the designs of more efficient strategies. Thanks for your listening, and I'm glad to answer any questions.
Please line up for your questions. Yes. Jeff Kenning, Harvey Mudd College. So obviously it's impossible to test everything. I'm curious how you decided what to test to start with. and now you've got some data that says what areas tend to fail. But how did you get started? And also, what sorts of things do you feel like you have not tested enough that you'd like to test more in the future?
If I understand your question correctly, you are asked which test cases we choose. Okay. Actually, in the basic testing configuration, we test every test cases provided by chip manufacturer. Yes.
Thank you.
Hi, Kevin Laughlin, University of Michigan and Google. Great talk, thanks for sharing, really enjoyed it. My question is based on the fact that a lot of my research has been on rowhammer bit flips, so bit flips in DRAM as opposed to CPU. And two observations from that line of work are that there are data dependencies, so there are data patterns that make you more or less likely to observe bit flips, and that as you've gone to newer DRAM nodes, more dense technology, it's increasingly vulnerable. So I was wondering if you had looked at either of those phenomena in the CPU world of bit flips, namely if newer, denser CPUs were more susceptible, and whether there were data dependencies for bit flips.
Okay. If I understand your question correctly, you are asked something about bit flip patterns. For example, maybe input data dependence on input data.
Yes.
Okay. As an example, we have tested something about the data dependence. For one SDC, we observe that if we input the certain input data, if we consider the input data, and that case that execution reproduce the SDC, the error, the bit flip precision is fixed. Yes, but in another SDC cases, it is no matter. We also do this experiment, but we found the bit flip position sometimes varies.
Got it. Thank you.
Let's thank the speaker once again.